Hello, and everyone. Welcome to the final session of the day in this room, using HashiCorp Vault with Kubernetes. My name is Seth Vargo. I'm a developer advocate for Google Cloud. You might recognize me from the DevOps versus SRE series, where we say class SRE implements DevOps. I'm excited to be here today. Prior to Google Cloud, I actually worked at HashiCorp. I worked for our other speaker, Armon Dadgar, who is the CTO and co-founder of HashiCorp. And I will bring him on stage in a minute to talk about Vault. Just a quick overview of today's agenda. We have 4 distinct sections. You'll recognize them by the colors that they're associated with here. We're going to start with a quick overview that Armon's going to give us. I know some of you might be familiar with Vault, but we want to make sure that we have a common baseline. Next, I'll tell you how to run Vault in Kubernetes as a service. We're going to get really technical, so I hope everyone's ready. There will be a live demo. Then I'll show you how to connect to that same Vault cluster using Kubernetes applications from different pods and different services, again, accompanied by a live demo. And then finally, Armon will talk about some of the new and exciting things that are coming on the Vault roadmap in the future. So with that, I'd like to welcome Armon on stage.
Thanks so much, Seth. I'm hopeful we will get through this session without running out of disk space, but fingers crossed. So like Seth said, what I was hoping to do was for folks who are less familiar with Vault, start off with a bit of a high-level introduction, right? What is the sort of problem motivation, right? I think we're probably all a little tool overwhelmed, so hopefully there's a good enough reason for us to sort of consider adding yet another. So before we really start talking about Vault, I think it's useful to talk about kind of the larger problem, right? Secret management as a whole, which is really what Vault attempts to solve. And so when we talk about secret management, I think the first question, kind of the most natural question, is what exactly are we managing? What is a secret, right? And so one of the things we talk about is, what is a secret and how is it different from sensitive information, right? So when we talk about a piece of secret information, it's something that allows us to either authenticate or authorize against the service, right? So an example might be a username or password, right? We can provide that to, let's say, a database to authenticate a session against that database, prove our identity, and then the database is allowing us to request data from it, right? Similarly, something like an API token, we can present that when we make a call up to, let's say, Google Cloud to read and write from Blob Store. It's authenticating the client. It's authorizing us to actually do that request. And finally, something like a TLS certificate, right? You might not log into a system exactly with a TLS certificate, but you're presenting it to a client, and that's authorizing you as, let's say, www.hashicorp.com. And so it's allowing us to sort of elevate ourselves into this trusted position. So any of these types of materials, right, username, password, certificates, are sort of secrets, right? And the reason we want to keep them secret is if they fell into sort of the wrong party's hands, they could use it as a mechanism to authenticate themselves or authorize themselves to perform actions they shouldn't, right? They are a mechanism of access, and so those mechanisms need to be tightly kept. On the other hand, we have sort of sensitive information, right? This is a little different because it's things that you'd like to keep confidential but can't directly be used to sort of authenticate, right? I can't use my customer's social security number to log into the database, right? But it doesn't mean I'd like that piece of information on the public internet. So it's important to make this distinction between sensitive things, which Vault can help us manage, and we'll sort of talk a little bit about how, versus secret things, which Vault intends to sort of put inside of it, right? You use it as a database to hold on to secret information. So when we go from saying, this is what a secret is, to then talking about secret management, the way I like to sort of talk about it is what are the set of questions we want to be able to answer, right? So when we talk about secret management, these are sort of the key ones, right? How do our applications get these secrets, right? My web application boots, it needs to talk to a database. How does it get a database password? On the same hand, how do our human operators get access, right? If I'm a DBA and I need to connect to the database to do some maintenance on it or fix some issue with it, how do I get that same database credential? Then how do we think about updating these things, right? We don't want them to be sort of static credentials that live forever. We want to be sort of periodically rotating them, whether for compliance or just good hygiene. So how do we think about if I change my database password, how does that impact my applications? How does that impact my operators? How do I actually automate that flow? Then there's sort of the bad things that could happen, right? What if this thing is compromised? How do I think about revocation of access, right? How do I do forensics on who's done what when if I'm trying to figure out, are we in a compromised situation? Where has this key leaked? And so what do we do in the event of a compromise? Everything from that forensic understanding to reacting to it to rotating it. So these are sort of the hard questions that we'd like answers to. So the state of the world, when we sort of generally talk about secret management as a problem, is not necessarily great, right? What we often describe it as is secret sprawl, right? This is a scenario in which secret material is sort of sprawled all over our infrastructure. It's hard-coded in source code. It's in plain text in our configuration. It's checked into GitHub in plain text. It sort of just litters everywhere, right? And the challenge with this is sort of it's very decentralized, and we have very limited access controls around it, right? Like who can access GitHub in an organization? Probably anyone with single sign-on, right? Who can see this plain text configuration? Who knows, right? It's not something we're tightly access controlling. And so we have limited access control around it, but also even worse visibility, right? So then if we actually wanted to do an audit of who all has looked at this particular source file in GitHub, do we actually have an ability to do fine-grained sort of auditing and forensics on that? So the state of the world, not necessarily great when it comes to answering some of those secret management questions. And so this is really where Vault enters. Vault's sort of original purpose was to try and look at secret management and say, can we provide a good answer to these set of questions? And so our goals sort of at the top line are starting with a single source of truth, right? How do we move away from this sort of decentralized sprawl to a world where that is centralized and managed in a single place, right? And so part of this is really understanding there's two different kind of consumers. There is our sort of application consumers that want programmatic access. The web server is going to boot. It wants to fetch a credential and do it in a sort of an automated way. It's not, we don't want sort of a point-and-click interface for that. So API-driven automated access for applications doing automation. On the flip side, we still have our human operators, right? They want something nicer than an API. They want command lines. They want user interfaces, right? And so we want these two access patterns to both be really optimized so that we have this single source of truth, and we want a solution that's cloud-friendly, right? So what that really means is it should be easy to operate. It should be not dependent on specific hardware that we need to deploy in a private data center. It should be sort of pure software that we can easily operate in a cloud environment. So then when we translate that into, OK, these are Vault's top-line goals, how do we actually achieve that? The sort of table stakes where things start is just a secure place to put bits, right? We want to put bits in, have it securely stored, get those same bits out, right? Whether that's, let's say, database username and password. And so in transit, when clients are talking to Vault, Vault forces sort of end-to-end TLS. Unless you change it by default, it asks for the highest level of 1.2. And everything at rest is encrypted and managed with AES, right? So we have AES 256-bit, both sort of encrypted and authenticated, so we can detect sort of tampering of data at rest. And this is exposed to the end user as sort of a hierarchical key value store. So you can apply some organization around folder structure and grouping things together in a way that makes sense for you. So just make this a little bit less theory, a little more concrete. Here's an example from the command line interface of both writing and reading a secret. So what we see here on the first command is we're doing a vault write against a path, secret foo. So like I said, it's sort of a hierarchical file system. So in this case, secret is sort of a directory, and foo is the sort of file, the leaf node we're writing to. And then we can write opaque values. So we're writing bar is equal to bacon. But you could imagine that would be, username is Armand, password is 1234, right, as an example. And then we can come back around, use the CLI, and do a read against that same path. So we're doing a read against secret foo, and what we see is we're getting back bar is equal to bacon. So what this is really masking for us is really thinking about, as a client, is this encrypted over the wire, right? The CLI is sort of talking over an encrypted channel to Vault, hitting its API. And then Vault is transparently doing the encrypt as it writes it out to disk, doing the decrypt before it provides it back to us as a client. So sort of doing the right things, making sure we're doing this with hygiene, but kind of making this easy as an end user. Just to illustrate the sort of equivalence of that, here's the same example as what we just did on the CLI, but hitting Vault's API instead. So like I said, one sort of primary consumer of Vault is our applications, our automation tools, and they want to consume it programmatically with an API. So here's just a simple example of doing curl, where we're basically doing a write against the same path of foo and encoding the data that we want stored, and then doing a read back against the same thing, right? So it's meant to be a simple RESTful API that's easy to integrate with. And so, that's sort of one level. That's sort of table stakes is, putting our secrets somewhere that we know it's encrypted. We have audit logging and access control around it, all that kind of good stuff. But there's still a bunch of sort of hard questions, right? There's questions like, what if an operator connects to Vault and they just find it annoying to have to go to Vault, so they're just going to copy everything out and put it in passwords.txt, right? So they don't have to bother log in. Or an application starts, and I'm sure we've never seen this. The first thing it does is write all of its configuration out to standard out or its log file, right? So it just reads all the database username and password, dumps that to disk, and ships that off to our central logging system in plain text, right? And the third sort of classic case is we hit a diagnostic error, right? It's a 500 error on rendering, or we're in a debug mode, and it says, here's my database username and password, by the way, right? If this helps you with debugging. So the thing you find is the entities we're sort of giving these credentials to, whether it's applications or operators, do a terrible job keeping secrets, right? So this kind of raises an interesting challenge of, how do we still protect these secrets even though all of these scenarios are, very likely? So Vault's approach to this, the way Vault thinks about this problem is, the challenge is we have these sort of long-lived static credentials, right? And the challenge with long-lived static credentials is if they leak anywhere ever, right, either through passwords.txt or through a log file or through a diagnostic page, it's sort of game over, right? We've arranged it as a zero-sum game, right? It's either a perfectly kept secret or the secret's out there and we're hosed, right? So how do we sort of reduce the stakes, right? How do we make this so less severe than all or nothing? And the way you have to do that is making secrets ephemeral, right? You don't want to have these long-lived credentials that are valid forever. You want these things to be short-lived, time-bounded things so that even if they get logged to disk, oops, right, they're only valid for so long before we've moved on to a different set of credentials. So Vault's approach to this is what we call dynamic secrets, right? And the idea is sort of as opposed to static secrets, what we want to do is generate a unique set of credentials on demand, right? So when a web server says, I want a database credential, we generate that credential as in point in time right there. We have a unique audit trail now that ties us back and says, this web server has this unique credential. And by the way, that's valid only for 24 hours, right? So when the web server renders a 500 diagnostic page and leaks out our database password, we've time-bounded how long that credential is valid before moving on to another credential, right? And if there is a breach and we know that that credential is exposed, we can revoke it early. So what does this actually look like from the perspective of a client? They're just doing a read against Vault in the same way we just saw before, where they just did a read of secret foo. And behind the scenes, Vault is then going out and talking to the endpoint, right? So it's going and talking to the database and saying, create a new dynamic credential, right? It's creating an audit trail of that credential, and then it's providing that credential back to the user, right? In this example, I'm using a database because I think it's sort of an intuitive one. But you can imagine this exact same diagram where you replace the database with any sort of endpoint system that supports credentialing, right? A prime example would be Google Cloud itself, right? So I want to give my application a credential that lets it read and write from Blob Store as an example, but I don't necessarily want to give it a credential that lives forever, right? I want to give it a credential that's valid for 24 hours, and I'm rotating that credential all the time. So in that same setting, Vault would connect to Google Cloud, generate a short-lived credential, create the audit trail, and provide it to the application or end user, maybe developers doing some debugging, right? So the sort of example holds. So let's see. So when we talk about the sort of secret backend approach, right? So far we talked about Google, we talked about using it with a database type system. But it's really a general idea, right? The general idea is any system that uses credentialing to manage authentication or authorization has this similar sort of a challenge, right? Which is our consumers need the credential so they can consume the endpoint system, but we don't want these things to be static. And so our goal with Vault is this is actually a plug-in point. It's sort of an extensibility point where over time we're sort of constantly adding new systems and adding support for them to be kind of consumed in this dynamic way. So cloud providers are one great example where they need API tokens to interface with, and maybe you're giving those to humans, maybe you're giving those to applications, maybe your automation systems are consuming it. How do we make sure that we don't have a forever token in Jenkins, right? Databases are a great example, systems of record that have data. But then you get into all sorts of other systems, right? Messaging queues, things like RabbitMQ, SSH, right? I mean, I think we could probably, maybe I'll spare everyone from raising hands, but I'm sure many of us have seen the master shared PEM file with a few hundred developers having access to the same PEM that secures a huge fleet, right? And so that's sort of an interesting challenge where we have this shared mechanism, this PEM file, that sort of too many people have access to. So the list sort of goes on and on. There's sort of other stuff that we don't have time to touch on in much more detail is sort of classic security bread and butter, right? The sort of 3 A's, right? As you'd expect, Vault has sort of many different mechanisms to authenticate against it. So whether it's an app running in Kubernetes and we're tying into the platform, it's a VM just running in Google Cloud, or it's a user who's using LDAP to authenticate, there's sort of many different authentication mechanisms. All of that comes into then sort of a central authorization system. So there's a central way in Vault where you authorize who's allowed to do what. So one huge goal with Vault is how do we get to sort of least privilege? You should only be able to access exactly what you need, not sort of everything because you were able to log in. So Vault has a very fine-grained Auth-Z system that lets you scope down who can do what based on their sort of identity. And then lastly is sort of rich auditing. So we want to have that audit trail of who did what when. Cool. And with that, I'm going to hand it back off to Seth, who's going to talk to us about how we actually use this and operationalize this within Kubernetes. Thank you.
Great, thank you, Armon. So the goal of the next section here is to really answer 2 questions. Why would I run this on Kubernetes? Is it a good idea? Should I? And how do I do it? The first answer is yes, so we'll move on to the second question. So what does this actually look like? So the following diagram here is also captured as code on GitHub, github.com/Seth Vargo/Vault on GKE. But I want to walk through it quickly together. And before I do, I want to mention that this follows the HashiCorp Best Practices Guide for production deployments and production hardening. This was built in kind of collaboration with some of the Google security engineers, as well as some of the people on the SIG security team on Kubernetes. So it represents what we like to think of as kind of the best practices way to run Vault on GKE or any Kubernetes cluster. So at the top level, we have some type of load balancer. In this example, we're using cloud load balancing because we're making this Vault server publicly accessible. In your own environment, you might want to use VPCs or VPN-type networking where it's only accessible in certain subnets. And then we have a highly available Vault cluster. So we might have 3, 5, 7 servers all running behind this load balancer. And then below that, we have obviously the Kubernetes engine itself. And then we're using Google Cloud Storage as the underlying storage backend. We also support Google Cloud Spanner. And we are using Google Cloud KMS to do the initial encryption of the initial root token and the initial unseal keys. So let's walk through some of those in a little bit more detail. So first, we're using a dedicated Kubernetes cluster. And there's a few reasons for this. But we don't want Vault running alongside the same Kubernetes cluster where your applications are running. In fact, we might even recommend running it in a separate Google project that only the security teams and the networking teams least privilege access. And to the other clusters and other application developers, Vault is just a thing at an IP address. We're leveraging Google Cloud Storage. Again, we could leverage Google Cloud Spanner, but both of those storage backends support high availability. As a production deployment, we need this to be highly available. There's no reason why we wouldn't. So we're going to leverage Google Cloud Storage for our high availability and our storage backend. Another advantage there is that we can back that data up. We can do replication. We can do customer-provided encryption keys as well. We're going to leverage Google Cloud KMS. Everyone taking a picture? Nice. We're going to leverage Google Cloud KMS because our Vault servers are going to be automatically initialized and unsealed. So those initial unseal keys and that initial root token eventually need to get into the hands of an operator or an automation system, but we don't want them stored in plain text. So we're going to leverage Google Cloud KMS to encrypt those values and put them in the storage backend. Additionally, we're leveraging our own custom certificate authority for TLS. So one of the questions I get is like, oh, why wouldn't you use Let's Encrypt? Let's Encrypt is amazing, but the problem is I don't actually want to trust any certificate on the internet. Instead, I want to use mutual TLS validation, and I want to use my own certificate authority and only trust certificates signed by that authority, not even my system certificates. This helps secure Vault and make sure that only people with the certificates and the proper certificate authority have the ability to communicate with this server. Additionally, we're leveraging L4 load balancing. Instead of using something like the global load balancer, the GLB, we're actually using regional load balancers. And the key reason here is that an L7 load balancer is going to do the TLS termination for us. And we don't actually want that. We want Vault to do the TLS termination, primarily so that Vault can handle mutual TLS authentication. But also, we don't want to decrypt data and then have a different re-encrypted connection on the back end, right? Using an L4 balancer lets us pass that through directly to Vault and lets Vault handle its own TLS. And if Vault ever rotates those TLS certificates that it's using, those automatically happen. We don't have to also rotate them in an upstream load balancer. And then lastly, and this is a really key point, we want to think of Vault as a service. right? So in my internal operations team or my internal security team, yes, I'm running Vault under Kubernetes, and I'm leveraging a lot of the functionality that Kubernetes provides. But ultimately, I'm delivering secrets as a service or secrets management as a service. So there's Vault and an API and an IP address. And users ultimately shouldn't care whether Vault is running on a VM or a container or bare metal, or it doesn't really matter. So we really want to think about this as Kubernetes is providing kind of the building blocks that let us run Vault as a highly available service. And we get some really cool benefits. One of them is you might see that we're going to leverage a stateful set here. And the first thing you might think of is like, wait, this isn't a database. There's actually no state. Vault state is stored elsewhere. It's stored in GCS. Why would I use a stateful set? And there's a few reasons why we might want to use a stateful set. First, it gives us predictable naming. Our actual container names will be like Vault-0, Vault-1, Vault-2. This is really helpful for debugging, audit logging, et cetera. The real reason, though, is that the stateful sets give us exactly once semantics for free. So as our servers are starting up, one will start up. It will unseal itself. It'll be ready to go. As soon as its health check is passing, the next one will move along. So we actually avoid any real-life race conditions with initialization or unsealing. The same is true for upgrading. You don't want to upgrade all of your Vault clusters at once, right? You generally want to upgrade one and let the leadership transition to a new server, upgrade that one, et cetera, until the entire cluster is upgraded. This is true with any software. Using stateful sets, a single change to the YAML file or whatever you're using for the description of this deployment automatically does kind of a rolling update. And if one of them fails, it'll stop. We get a free circuit breaker pattern. So there's a lot of reasons why we might want to use a stateful set here. Additionally, we're leveraging anti-affinity rules. So anti-affinity rules are a Kubernetes feature which let us do things that affect or influence the pod scheduling. By default, if we did not have this YAML here, Kubernetes would put all 3 Vault containers on the first node. And that's not highly available, right? If that one VM dies, we lose all of our Vault servers. So what we're doing is leveraging anti-affinity, basically suggesting to Kubernetes, or in this example, requiring Kubernetes, to spread these across all of our available nodes or hosts. This means if one VM dies or 2 VMs die, that our Vault servers, the actual containers themselves, are spread across the node pool. So this adds an additional layer of availability for us. We're also leveraging auto-unsealing. The auto-unsealing is also an auto-initializer. This allows you to spin up a Vault cluster very quickly without operator intervention, and the keys will be encrypted with KMS and put in the storage backend. We're also doing some little things that make a big difference. For example, we're giving the container the IPC lock capability. By default, Vault supports memory locking. This is something that Vault does in its code base. Containers don't give you that privilege by default. So we explicitly ask Kubernetes to give our containers the ability to do memory locking. Again, just an added layer of security. And then our readiness check is basically asking Vault for its own health, but we explicitly want to make sure that our standbys are also added to the load balancer. Because this readiness check here is going to determine when the container is able to receive requests from the load balancer. And we want to make sure that our standby servers are also able to receive requests so that they can forward them appropriately to the leader. Notice that we're communicating via TLS. And then lastly, as we saw in the diagram, we have this load balancer. Again, this might be an internal load balancer in your own VPC, or it might be a public-facing load balancer. I don't recommend that, but there's no reason it can't be. So with that, let's jump over to demo 1. So if we can switch over to the laptop. All right, here we go. Did everyone pray to the demo gods? Here we go. All right, so the first demo here, I'm just going to show you what it's like to run Vault as a service on Kubernetes, basically using those exact YAML files that I just showed you. First, I want to show you I have a Kubernetes cluster here. It's running on GKE. So we'll go to Kubernetes Engine, and we'll take a look at the workloads here. And there's nothing, right? We have no workloads here. We haven't deployed Vault yet. So what I'm going to do is over here, I'll just take a look at my vault.yaml. And you can see that this is very, very similar to what I just showed you on the slides. There are some additional pieces of information here, like I'm deploying a replica set of 3. So I'm going to have 3 Vault servers. Again, there's that anti-affinity that we saw before. And all of this is open source, by the way, so don't feel like you have to capture all of this right now. We have our first container, which is our init container. That's going to do the Vault initialization. And then we have some configuration for that container. And then we have the actual Vault server itself. We're pulling that directly from the Docker Hub. Again, there's that IPC lock capability. And we're opening some container ports that'll be available for requests, some basic memory and CPU requests, and then again, some configuration. And here you can see where we're actually supplying Vault its startup configuration via the magic Vault local config environment variable. So we don't have to worry about writing out a file to disk. We do this all kind of in the environment variable. So with that, let me go ahead and apply this. So I'm terrible at typing, so I wrote fancy scripts for y'all. So what this is going to do is it's going to just grab that Kubernetes endpoint, and it's going to apply kubectl apply-f that particular stateful set. So what we should see here in a second, and this is where everyone's prayers would be helpful. OK, there we go. So these pods are actually starting up. And you'll notice that 1 of 3 of them are starting up. And that's because we're using the stateful set, which is doing that one at a time exactly once semantics. So Vault 0 is running. It has some warnings. But I think that's just because it's booting up. And if we go back, we'll start to see, hopefully, OK, Vault 1 is starting as well. And then once we get to Vault 3, this entire replica set will be happy. And at that point, we will have a Vault cluster. Because what's actually happening under the hood is we're not just running that Vault container. We're also running that Vault init container. And because this is a fresh, new container, it's actually creating the storage, connecting to the storage backend, doing the initialization, putting those unseal keys encrypted via KMS into that storage backend, as well as the initial root token. And then the other servers, when they start up, they look and they say, oh, I'm already initialized. They grab those encryption keys and do automatic unsealing for themselves. If we were to scale up or scale down the cluster, because the initialization has already happened, the initializer will just unseal them. It won't actually do the initialization anymore. So let's go ahead and refresh this and check where our status is. I see a green check mark, which is great. I'm going to go ahead and jump over to Google Cloud Storage here. Just real quick to show you all. So this is the storage bucket that I'm using. And in here, you'll see the folders here, core and sys, which are created by Vault. But then the root token and the unseal keys are both encrypted via Google Cloud KMS. And then they're stored in this Google Cloud Storage bucket. So when I want to interact with Vault as an operator, I need to download those via like GSUtil or via the Google Cloud API, decrypt them using Google Cloud KMS and the proper IAM permissions. And then I can interact with Vault directly. So let me go ahead and switch back to Kubernetes, and I'll show you what all of that looks like. So I'm going to jump over here. I have another magical shell script, which I will show everyone. So this is my magical shell script where I super can't type. But basically, all of this does is it grabs the CA certificate. Again, we're using a custom CA. So putting the output of that, the address to my Vault cluster, and I provision this Vault cluster with Terraform, so I'm delegating to Terraform there. And then the token decrypt command, which is just a really long GSUtil command with some base 64 and some gcloud KMS. So what I'm going to go ahead and do is run this. And again, this is all open source. Oh, look, see, I left myself this note because I knew I was going to mess it up. This is when you know you've done too many demos. So this takes a little bit because it's actually making like about 5 or 10 API calls, but great. Now what I can do is I can actually just run env grep Vault. We see that we have our Vault token, our Vault adder, and our Vault CA cert. These are magic environment variables that Vault reads. I could also supply them via the CLI, but I'm lazy. So now what I can do is hopefully I can run Vault status. And look at that. We now have a Vault cluster up and running, 5 key shares, a threshold of 3. It's in high availability mode. And this particular node I hit is in standby. So if we look at that second to last line there, we'll see that this particular node that we hit is in standby. If I run Vault status again, now I hit the active node, coincidentally, because we're doing round-robin load balancing on that load balancer there. Anytime I make a request to a standby, that standby will automatically forward the request to the active leader. So I don't have to know where the leader is. I just know the load balancer address. So this is how you run Vault as a service on Kubernetes. If I kill one of these pods, it'll automatically restart. It'll maintain a quorum of 3. When it comes back online, it'll be automatically unsealed. And until that point, it won't be added to the load balancer as well, which is why that health check is so important. So with that, can we jump back to the slides? Awesome. So that concludes the first demo. You can clap. So now we have to forget everything. Forget everything you just talked about, because the next section is, now that I have Vault running, how do I connect to it from Kubernetes? But I want you to forget that Vault is running in Kubernetes. Think it's running, in some third-party service like Heroku, or it's running on VM somewhere. Forget that Vault is running in Kubernetes. Instead, Vault is just a thing available at an IP address. Everything we're about to do can work with any Kubernetes cluster. We're going to use GKE, but it could work with your on-premise Kubernetes cluster, et cetera. So again, forget that Vault is running on GKE or Kubernetes. It's just a thing at an IP address. Because the next thing we're going to do is create another Kubernetes cluster. All right. Clicky. All right. So very quickly, we have to talk about Vault authentication methods. So Armon mentioned this very briefly in the beginning. Authentication in Vault is the process by which users or machines supply information to Vault. Vault verifies that information with either internal data or some external third party. And then, assuming that is valid, converts that into a token with policy authorization attached to it. Here's an example of what that looks like kind of in a graphic form. We have the Vault server in the middle, which would receive a request from a user or a machine or an application. It would then take that information to this third-party system. That, assuming that's successful, it would go to its own policy engine and map that to a Vault policy, and then return the token, which is kind of like a session ID or a session token, to the user, which would then be used for all future requests. It's like logging into a website. You know, sometimes you log in with a username and a password, and your browser sets a session ID. But sometimes you can also log in with Twitter, or log in with GitHub, right? Vault is conceptually similar to that. So what does that look like with Kubernetes? Well, it's actually very straightforward. We just replaced that third-party system with a token reviewer API from Kubernetes. So a user, or in this case, a service account representing a user or a pod, makes a request to the HashiCorp Vault server with their service account token, their JOT token. That JOT token is given to the token reviewer API. The token reviewer API verifies that JOT token's validity and timestamp, et cetera. And assuming that's successful, it goes back to Vault and says, yep, this looks great. Vault then goes to its own internal policy engine and says, oh, OK, well, the things in this particular namespace get this particular policy attached to them. Here's a Vault token with that policy attached. And this is how the Kubernetes auth method works at a very, very high level. There's technical details here, which we're not going to get into. But this is at a very high level how this functions. So to do this, you could write your own little bash script. Or I've actually open sourced the Vault Kubernetes Authenticator, which does this whole process for you. It will grab your service account from var run Kubernetes secrets, the service account JOT token. It will post that up to the Vault server, which is configured via an environment variable. It will get the token back, and it'll put it in an in-memory volume mount for you. So then all your applications and services have to do is extract that token from that in-memory volume mount. So you don't have to actually think about Vault authentication in Kubernetes anymore. You could just leverage this and know that the token will be there, assuming authentication was successful. It runs as an init container, not a sidecar container. So it must succeed in order for the other containers to run. Then we leverage tools like console template. So despite its name, you don't need console to use console template. But console template is a tool that is designed to provide a configuration language by which we extract secrets and credentials from Vault and present them kind of on disk or on a temp disk or an in-memory disk to an application or service without the application or service knowing that it's communicating with Vault. Many of you have brownfield applications or even greenfield applications that you likely don't want to directly integrate with Vault. You might not want to call the Vault API directly using the Golang library or the Ruby library. Instead, you might want to just continue to leverage a file system or environment variables for credentials. And we like that abstraction, because then you're not tightly coupling your applications to a secret manager. Instead, you're saying, my config is on disk, or my config is from an environment variable. What console template allows us to do is to provide that same experience, but under the hood, as a sidecar application, it is actually managing the connection to Vault, the renewal, and the acquisition of all of those secrets, and, as we'll talk about in a minute, what happens when those secrets are revoked or are rotated. So I know what you're thinking, right? What happens, though, if my credentials change? So I have this sidecar application that wrote this file out, and my application is reading those credentials from that file, but how does this console template thing actually inform my application that my credentials have changed? So let's think of a real-world scenario. I have a database credential. Vault tells me that database credential is valid for 24 hours. At the end of 24 hours, Vault is going to revoke that credential if it's not revoked earlier by an operator. At that point, my application, or console template, has to go back to Vault and say, OK, I'm still authorized. I would like another database credential. And it'll be different. It'll be a different username and a different password. So I'll write that out to my config file. But my application has probably already loaded its config. right? Most web applications don't go to disk and read their config at every user request. They load that into memory, and they kind of cache it until they're restarted or receive some sort of signal. So how can console template signal my application to reread its credentials? We're in a Kubernetes world where all of those containers are isolated. Well, an interesting feature, an alpha feature right now in Kubernetes, is this idea of shared process namespaces. So shared process namespaces are the solution to this challenge. And again, this is an alpha feature, so it's available in GKE alpha. And if you're running your own Kubernetes clusters, you'll have to enable it with kubadmin or a similar tool. But this shared process namespace allows our containers to communicate with one another. So instead of having every container be PID 0 or PID 1, they're actually a root container and then these subcontainers with the ability to communicate with one another. So if we give our console template process the sysptrace syscall, the security context capability, we can actually leverage the standard Unix tools like pidof and kill to signal applications. And then all we have to do is provide a command to console template, and it says, hey, when this file changes, or when this environment is updated, or this secret is revoked, just send, in this example, hup to the PID of my app. We can leverage the built-in pidof tool for that, right? Or perhaps it's something more complex, right? We might have some 50-line bash script that we have to run because of some arcane Java-based application that is very finicky, right? We capture that as code, and console template executes that for us. So this can either be as simple as a signal, or it can be as complex as a very systematic and procedural restart. So with that, let's go ahead and jump over to the laptop, and we'll take a look at what Demo 2 is. So what I'm going to do here is, in the Google project switcher, I'm actually going to switch to a different project. So I have another project here called My App. So I'm in a completely different project now. Remember, one of our best practices we recommended earlier was that we have a dedicated project and a dedicated Kubernetes cluster for Vault. And then we're only thinking about Vault as a service right now. It's just a thing at an IP address. So I have this other Kubernetes cluster where I run all my applications and services for production. All my web apps, all my stateless services, all my stateful services, they're all in this My Apps Kubernetes cluster. Right now I don't have any apps, but we're gonna create a few in a second. All right. So I have a few scripts here. The first is we're going to set up the Kubernetes auth method. What the Kubernetes auth method is going to let us do is, like we described in that diagram, it's going to configure Vault to talk to the Kubernetes cluster with the right certificate authority so that we can verify via the Token Reviewer API the JOT tokens. So let's go ahead and run that. So it creates a CRB and a few other things. And then we actually configure the Kubernetes auth method, and we create a new role for authenticating to that configuration. So now, at a very high level, what this means is when I have a pod in my cluster, and it goes to Vault with its service account, that service account will be authenticated to get a Vault token back with a predefined policy that I've configured. So this is configuration that you could capture as code, or you could run it manually via the API. But then next what we want to do is we want to configure our GCP secrets. So the use case here is that Armon's example was database credentials. You might be Postgres or MySQL, et cetera. One of the other secrets engines that we have for GCP is the IAM GCP secrets engine. This lets you programmatically generate both service accounts and service account keys for GCP. So instead of going into the web UI and clicking and or using the API directly, you can programmatically generate on-the-fly tokens that are very short-lived for interacting with the GCP API, the same way that you might generate like an AWS access key. But we can do that with the GCP API. So what I've done here is I've just configured Vault very briefly to interact with those systems. So the last thing we need to do then is actually apply our application. So let me show you what our application looks like. So I'm doing a bunch of stuff here. All of mostly is just because I'm really bad at typing. But I'm grabbing the credentials from our cluster, and then I'm setting the context, and then I'm applying this Kubernetes YAML file. So take a look at that YAML file here. Kate's. So there's a few things that I want to point out here. The first is that we're running a pod now. We're no longer running a stateful set. This is just like a straight up pod. It could be replicas, but there's only one at this point. We're leveraging that shared process namespace. Again, this is important so that we can signal our application so console template can talk to our other process. We have a few volume mounts. We have our secrets. This is where console template's actually going to write its configurations, because they're going to be secrets there. We have our own TLS configuration. This is how our pod talks to Vault, because, again, we need that certificate authority and client-side TLS cert. And then the Vault token, which is an in-memory volume mount where the token will be written. So that never gets persisted to disk. We have our init container here, which is, again, just pulling from the Docker Hub. And we have a few volume mounts there. We set some environment variables, like where is the Vault server, where is its CA certificate. And that's going to run at boot. And assuming that's successful, it'll put our Vault token at a well-known path on disk, /home Vault. And at that point, all of our other containers, in this example, console template, can then pull that container, that token from the in-memory file system and interact with it. So here we have console template. We've given it the sys ptrace capability so that it can signal our other application. And if we scroll down here a little bit, again, same volume mount, same configuration. And then here's our console template configuration. And at the very end here, you'll notice that we have our arbitrary command. Our arbitrary command is just to send kill-hup to the PID of our Vault demo app. And then, as you might suspect, the last thing in our configuration here is our Vault demo app itself, which is just getting pulled directly from the Docker Hub. And actually, all it does is log its own file, so it's not very exciting. But it's really good for demonstration purposes. So let me go ahead and apply this now. So now if we go back here, we should see this workload start to provision. And you'll see that the pod is initializing. And if I'm fast enough, I wasn't fast enough. If you're fast enough, you can see that it's waiting for the init container to run. But if we take a look at this init container, and I'm using Stackdriver logging here, so you actually see the logs directly in the Google Console UI here. We see that a few seconds ago that the init container successfully stored the Vault token. So it did that whole walkthrough of going to the Vault server, presenting its JOT token, interacting with the Vault cluster, and then what we presented to console template was just a Vault token at a well-known path. Console template then grabbed that Vault token and used that token to interact with the Vault API to grab our service account key. So now when I go back to my pod and refresh this here, we can see that both console template and my app are running. And if we take a look at the logs for all of these, you'll notice that console template sent a signal to my app, causing it to reload. So at boot, console template detected a change in configuration. There was no config, and then it went to some config. So it sent the hup signal to the Vault demo app. The Vault demo app, or my app in this log, got that signal and printed out a log line that it reloaded. What you see here is a soon-to-be-revoked access credential for interacting with this particular GCP project. This is an actual IAM access token for interacting with GCP. I'm aware of this. I will revoke it, but it's cool. So I'm showing it to all of you. And what's happening is at some interval, this token just gets printed out basically every 30 seconds. However, at the end of about 5 minutes, what will happen is Vault will revoke that token. So by default, like GCP IAM credentials live forever until a human comes in and deletes them. Vault actually enforces a lifetime, and it makes the necessary API calls to Google Cloud to revoke those credentials when time permits. So unfortunately, we're running short on time, so I can't actually wait and show you that. But if we can switch back to the slides very quickly. So the last section now, I'd like to invite Armon back on stage to share a little bit more about the Vault roadmap and the future. So Armon.
Thank you. Awesome. Oh, we are definitely running short on time. OK, we're going to make this light speed. So thank you, Seth, for walking us through a little bit more hands-on than I had a chance to go to in terms of how we actually work with it. Some of the stuff I wanted to talk about, so for folks that are maybe familiar with Vault, have already used it, I wanted to give a little bit of a sneak peek in terms of kind of where Vault's going, sort of a little bit of our thinking in terms of directionality. I think one of the things that's sort of become clear to us, right, is that when we talk about this space, right? Secret management, tools like Vault, integrating it with these platforms it's complicated, right? And I think you kind of saw a snapshot of that. It's not exactly simple and obvious how all of these things kind of come together, because it's a hard problem we're trying to solve, right? We're trying to solve the problems of application identity, brokering between many different systems that don't necessarily understand each other, right? Like Postgres has really no idea what Google Cloud's IAM model is, and vice versa, right? So what we're trying to do is solve this challenge of each of these systems implement different mechanisms of access control, and we're sort of brokering between them, right? So it's a complex problem, and so how do we start making that sort of a little bit simpler? So one of the things we're starting to work on within Vault itself is, I jokingly refer to it as sort of Clippy for Vault, is you can kind of see a kind of a little pop-in wizard in the corner here, which is, it looks like you're trying to configure Vault. Can I help you with that? But sort of in sort of more seriousness, how do we sort of help guide users through, hey, these are the different kind of core workflows in terms of how do you configure Vault to understand Kubernetes as an authentication backend? How do you configure Vault to integrate it with Postgres? How does the sort of role mapping work between this? And so it's sort of meant to be a unobtrusive kind of wizard-like capability for different workflows that you can sort of enable as you sort of hit them to say, hey, please walk me through how this is supposed to work, and have it be a little bit more interactive as you're getting started with the system. Another common challenge we see with Vault is, how do I go from sort of, I think Seth did a great job laying out what's a best practice deployment guide look like in terms of isolating it with a separate cluster and treating it as sort of just opaquely living behind a load balancer and sort of building HA. And so that an interesting pattern is, how do we go from providing that sort of service, Vault as a service, for a single application owner or single sort of group, to all of a sudden many application owners, many groups, right? We want to sort of Vault as a service to be highly multi-tenant between many different potential groups or lines of business. And so one approach to this, the kind of historical approach, is you lean on Vault's very sort of fine-grained capability and authorization system. So you can segment out different parts of the system. Maybe you say, Eng star is managed by one set of people, and marketing star is managed by a different set of people, right? And we sort of segment using Vault's sort of hierarchical folder structure. Another sort of capability, a different way of thinking about it, is sort of full namespacing. And this is what's coming on our roadmap, is the ability to kind of carve out entire namespaces within Vault and say, I don't want to think about sort of managing permissions of these folders. I want to just carve out a whole namespace and say, this belongs to engineering, this belongs to marketing, this belongs to sort of another team. And those teams can then sort of sub-administer these namespaces independently. So looking at, as we go and think about Vault as a service, how do we scale up the number of kind of consumers, the different sort of folks who can be onboarded onto this service? Lastly is, some of the challenge around integrating with Vault, I think, as Seth highlighted, is there's this sort of tension between what we'd like to be able to do is maintain sort of operational flexibility, right, and not tightly couple our applications. We don't want all of our applications to embed Vault SDK and directly talk to the API and have to be sort of highly Vault aware, right? That sort of limits our operational flexibility. So instead, we'd like to decouple that and use tools like console template and scripts like Seth's auto initializer to sort of thread through the right credentials so that our app boots, reads its secrets, and is sort of blissfully unaware. A really common challenge, though, is how do we do that authentication before we can actually read secrets, right? And so one of the things we're starting to work on, and it actually just shipped this morning in sort of beta, is the Vault agent, right? And so this is sort of an optional agent you can choose to run alongside Vault Server, which you sort of have to run. And what it does is manage some of that flow for you, the flow of fetching the JOT, authenticating against Vault, periodically re-authenticating, integrating with tools like console template to be able to generate, and put configuration on disk in a more sort of application-friendly format. So these are some of the goals of the agent, is making it sort of easier to authenticate, easier to manage token renewal, easier to sort of cache some of this data locally, and then making those integrations a little more out of the box. So this is something that just shipped today, so if this is something that you find useful, please feel free to play with it. So with that, thank you guys so much for sitting through with this and joining us, and thank you to Seth as well for helping with this.